The Toruń Road Bridge project was an essential component of the operational program Infrastructure and Environment for the period 2007 to 2013, co-financed by the European Union's Cohesion Fund. The project's primary objective was to build a new bridge over the Vistula River and create a network of access roads to enhance the city's connectivity and transport infrastructure. This strategic investment was driven by the need to alleviate traffic congestion, improve transport efficiency, and foster economic growth in the region. The bridge, named in honor of General Elżbieta Zawadzka, spans a total length of 540 meters, making it the largest arch bridge in Poland. The most remarkable feature of the bridge is its main span, which measures 270 meters, setting a record for arch bridges in the country. Weighing over 10,000 tons, the structure quickly became a modern landmark and a symbol of Toruń's urban development. The construction of the bridge incorporated several advanced engineering solutions and unique design elements that addressed the project's structural and environmental challenges. The bridge's main structure consists of steel arches that rise elegantly over the Vistula River, supported by foundations reinforced to withstand various load conditions and environmental factors. A critical part of the project was ensuring the stability of the arches and mitigating the risks posed by factors such as flooding, river currents, and soil instability. The foundation and piling techniques employed in the construction of the Toruń Road Bridge were critical to ensuring the stability, durability, and overall success of the project. Given the challenging conditions of the Vistula River, a comprehensive and planned approach was adopted for the bridge's foundations to secure the structure against dynamic environmental forces and heavy traffic loads. The foundation work involved the extensive use of prefabricated piles, which varied in length based on the specific soil conditions and the required load-bearing capacity. Prefabricated piles were chosen due to their reliability, ease of installation, and efficiency in handling varying subsoil conditions. The varying lengths of these piles were strategically determined through thorough geological assessments and soil testing, which revealed differences in soil composition and stability across the construction site. To install the piles, specialized pile-driving equipment was employed. This machinery drove the piles into the ground to predetermined depths, ensuring that each pile reached a stable, load-bearing layer of soil. The installation method was carefully monitored and adjusted as necessary to maintain optimal alignment and achieve the required levels of penetration. This step was critical to securing a firm foundation for the bridge's superstructure, as the piles would bear the combined weight of the bridge and its anticipated traffic loads. To confirm the reliability and stability of the installed piles, the construction team conducted rigorous load-bearing tests. These tests were essential to verify the pile's capacity to support the structural weight and withstand external forces such as dynamic loads from vehicular traffic, shifting river currents, and environmental factors like flooding or soil erosion. The load-bearing tests involved applying incremental loads to select piles and measuring their responses. This process helped assess the pile's ability to transfer loads effectively to deeper, more stable soil layers. By performing these tests, engineers could ensure that the foundation could handle the projected weight and withstand long-term operational stress. Any pile that did not meet the necessary standards was either reinforced or replaced to guarantee the stability and integrity of the entire foundation system. For the central pillars located within the riverbed, the construction required specialized cofferdams to create a dry working environment. A cofferdam is a temporary enclosure, usually made of interlocking steel sheets, that is driven into the riverbed to form a watertight barrier. The enclosed area is then dewatered, creating a dry worksite within the river, which allows workers to construct the pillar's foundations safely below the water level. The construction of the cofferdams was a complex process due to the river's depth, flow rate, and variable soil conditions. Engineers carefully designed the cofferdams to resist the river's hydraulic pressure and maintain stability during the foundation work. Once the cofferdams were in place and the enclosed areas were dewatered, the workers excavated the riverbed to reach the appropriate depth. After excavation, they installed the prefabricated piles or poured concrete to create solid foundations for the bridge's central pillars. The use of cofferdams posed several engineering challenges, particularly in maintaining the structural integrity of the enclosures against river currents and water pressure. Additionally, there were risks associated with soil erosion and sediment displacement, which could undermine the stability of the foundation. To address these risks, engineers employed advanced monitoring systems to track water levels, hydraulic pressure, and soil conditions within the cofferdams. Moreover, to enhance the durability of the piles and foundations, various protective measures were taken, applying anti-corrosion coatings and implementing drainage systems within the cofferdams. These precautions were necessary to ensure that the foundations remained stable and protected from potential deterioration due to prolonged exposure to water and moisture. The large steel arches were manufactured in segments and assembled at the construction site. Transporting and positioning these massive elements presented significant logistical challenges due to their size and weight. To address this, the project utilized a combination of road and river transport, ensuring that each segment reached the assembly site intact and on schedule. Specialized floating supports were employed to facilitate the installation of the arches, which were then meticulously aligned and welded to ensure structural integrity. A particularly innovative aspect of the bridge's construction was the suspension bridge segment, which is supported by two towering pylons. This segment was designed to provide additional clearance for river traffic and to minimize the environmental impact on the riverbed. The design incorporated various corrosion protection measures to extend the bridge's lifespan and reduce maintenance costs. One of the most significant challenges in the project was the need to adhere to strict environmental regulations, as the bridge was constructed in an area protected under the Natura 2000 network. This designation required careful planning and continuous monitoring to minimize the ecological impact on the surrounding habitat. The project team collaborated closely with environmental inspectors and experts to ensure compliance with regulations and to implement measures that would protect local wildlife and vegetation. The construction methods and materials were selected to minimize the project's environmental footprint. For example, the use of prefabricated elements reduced the amount of on-site construction activity, thereby minimizing disturbances to the riverbank and surrounding areas. Additionally, temporary access roads and protective barriers were established to prevent soil erosion and protect water quality in the Vistula River. Supporting infrastructure and road networks beyond the bridge itself, the project encompassed a comprehensive network of supporting infrastructure, including approach viaducts, interchanges, tunnels, and local roads. These elements were critical to improving traffic flow and accessibility within Toruń, ensuring that the bridge served its purpose as a key transport artery. The project included the construction of 4 approach viaducts, each designed to integrate seamlessly with the bridge and the existing road network. These viaducts incorporated advanced geometric planning to accommodate various traffic scenarios, ensuring smooth transitions for vehicles entering and exiting the bridge. The road network also included a 3-level interchange, which provided efficient connections to local roads and highways, reducing travel times and congestion. Pedestrian and bicycle infrastructure, recognizing the importance of sustainable transport options, the project incorporated dedicated paths for pedestrians and cyclists. These paths were designed to provide safe and convenient access to the bridge, encouraging non-motorized modes of travel and enhancing the overall accessibility of the city. Logistical and technical execution. The execution of the Toruń Road Bridge project involved extensive planning and coordination among multiple contractors, suppliers, and government agencies. At its peak, the construction site employed around 2,000 workers, who collectively managed an area of over 400,000 square meters. The project's scale and complexity demanded precise logistical management, particularly in terms of material transport, equipment deployment, and construction scheduling. Complex geometry and advanced analysis. The design and construction of the bridge required advanced structural analysis and modeling to address the complex geometry of the steel arches and supporting elements. Engineers utilized state-of-the-art software and computational methods to simulate the behavior of the bridge under various load conditions, allowing them to optimize the design and ensure its safety and durability. Economic and social impact. The completion of the Toruń Road Bridge has had a transformative impact on the city's transport infrastructure and economic development. By improving connectivity across the Vistula River, the bridge has alleviated traffic congestion, reduced travel times, and enhanced access to key commercial and residential areas. These improvements have contributed to increased economic activity, job creation, and tourism growth in Toruń. The bridge has also become a prominent architectural landmark, symbolizing the city's progress and modernization. Its distinctive design and innovative construction techniques have earned recognition within the engineering community, further establishing Toruń as a center of infrastructural excellence in Poland. A comprehensive overview of the Toruń Road Bridge project, highlighting its engineering achievements, environmental considerations, and logistical challenges. The project's success can be attributed to a combination of innovative design, planning, and effective collaboration among stakeholders. As the largest arch bridge in Poland, the Toruń Road Bridge stands as a testament to modern engineering and a symbol of the city's ongoing development. The project not only addressed critical transport needs, but also demonstrated a commitment to sustainable infrastructure development, setting a benchmark for future projects in the region. Through its careful balance of technical complexity and environmental responsibility, the Toruń Road Bridge has become a lasting legacy for Toruń and an inspiration for infrastructural advancements across Europe. The Honam high-speed railway is a major infrastructure project in South Korea, designed to enhance connectivity and transportation efficiency within the Honam region. One of the key components of this project is the Mankyeong River Bridge, which lies in Section 3-3. The construction of this bridge is crucial for ensuring a seamless high-speed railway route, and it employs the PSM, precast span method, a modern construction technique that is revolutionizing the bridge building process. The Mankyeong River Bridge is an essential section of the Honam high-speed railway, a project aimed at providing faster and more efficient rail services across the southwestern regions of South Korea. The bridge, located in the third segment of the project, is strategically significant as it spans the Mankyeong River, a key waterway in the region. The successful construction of this bridge is vital for the continuity and stability of the railway line, allowing trains to travel at high speeds without interruption. The construction of bridges for high-speed railways requires precision, efficiency, and adherence to stringent safety and quality standards. The Mankyeong River Bridge is no exception, and the project team has adopted the PSM, precast span method, to meet these high standards. The PSM, precast span method, is an innovative bridge construction technique that involves the off-site production of large, precast box girders. Each box girder has a span length of 25 meters, and they are manufactured at specialized factories. The use of a controlled, factory-based production environment ensures high precision and consistency in the quality of the girders. The produced girders are then transported to the bridge construction site using specialized equipment and installed on-site. High quality and precision. One of the key benefits of the PSM method is the strict quality control that is maintained during the off-site production of the box girders. Factories are equipped with state-of-the-art machinery and have optimal environmental conditions to manufacture girders with precise specifications. This reduces the likelihood of defects that can occur during traditional on-site construction. Reduced construction time. The factory-based production of girders allows for simultaneous on-site preparations while the girders are being manufactured. Once ready, the precast girders can be swiftly transported to the construction site and installed. This parallel workflow significantly shortens the overall construction timeline, which is critical for large infrastructure projects like the Honam high-speed railway. Enhanced safety. Since the heavy lifting and girder assembly are done in controlled factory settings, there is less exposure to hazardous on-site activities. This reduces the risks associated with high altitude and heavy lifting work, ensuring better safety for construction workers. Environmental and cost benefits. The use of specialized equipment for transporting and installing precast girders minimizes the need for extensive on-site concrete pouring and curing. This reduces environmental disruption and makes construction less weather-dependent. Furthermore, the streamlined production and installation process can lead to significant cost savings. For the Mankyeong River Bridge, the PSM method was chosen to address the challenges posed by the river's width and varying terrain. The 25-meter-long box girders were carefully designed designed and manufactured in a factory, following rigorous quality standards. Special vehicles and lifting equipment transported the precast girders from the factory to the site. Given the span length of 25 meters, the project team was able to transport and install the girders efficiently, ensuring that the bridge construction adhered to the strict timelines and specifications set by the project. The use of the PSM method for the Mankyeong River Bridge has ensured minimal disruption to the river environment, reducing ecological impact while maintaining construction efficiency. Additionally, the high precision of the precast girders has led to a durable and robust bridge structure, capable of supporting the dynamic loads imposed by high-speed trains. The construction of the viaduct over the Ferreira River in Guntín, Lugo, is a significant engineering project that demonstrates modern bridge building techniques. This viaduct is a hyperstatic structure, designed with 5 spans, with lengths of 45, 60, 60, 60, 45 meters respectively. It features a double carriageway and reaches a maximum height of 60 meters, showcasing a complex assembly process that required precision and innovative equipment. The viaduct is classified as a hyperstatic structure, which means it has more support constraints than necessary for its stability. This characteristic allows the bridge to distribute loads more effectively across its multiple spans. The 5 spans of varying lengths enable the viaduct to cover the river and its adjacent terrain while ensuring structural integrity and aesthetic coherence. With the maximum height reaching 60 meters, the viaduct needed careful planning to minimize environmental impact while offering structural safety. The choice of span lengths, 45 to 60, 60 minus 60 to 45 meters, suggests a balance between material optimization and structural efficiency, reducing bending moments and deflection. A beam launcher played a crucial role in the assembly of this viaduct. A beam launcher is a specialized piece of equipment used to place large prefabricated beams precisely in their final positions. In this project, the beam launcher was employed to install the beams over the Ferreira River without the need for temporary scaffolding or extensive ground-based support structures, which would have been challenging due to the river and surrounding terrain. This technique is especially beneficial in projects like this, where environmental preservation and site access pose constraints. The beam launcher, essentially a mobile crane on tracks, moved along the spans as it lifted and positioned the large beams. This process allowed the construction team to maintain high levels of precision while avoiding potential disruptions to the river ecosystem. The use of such equipment is both efficient and environmentally conscious, reducing the need for temporary foundations and scaffolding that can disturb sensitive landscapes. The double carriageway design enables a higher traffic capacity, catering to modern transportation needs. Additionally, the hyperstatic design enhances the viaduct's durability and resistance to external loads, such as wind, seismic activity, and heavy traffic. By distributing forces effectively, the bridge gains a greater margin of safety and longevity. The viaduct over the Ferreira River in Guntín, Lugo, exemplifies the integration of modern engineering principles and advanced construction techniques. The use of a beam launcher for its assembly was crucial in overcoming environmental and logistical challenges, resulting in a resilient and aesthetically balanced structure. This project is a testament to the progress in viaduct construction, combining innovative machinery with a deep understanding of structural behavior to create a safe and sustainable infrastructure. The Junior Sasaguri Station Pedestrian Overpass Installation Project represents a significant undertaking aimed at improving both accessibility and safety for passengers at the Sasaguri Station, located on the Junior Sasaguri Line in Japan. As stations become increasingly busy and passenger flow intensify, the necessity for safe and efficient crossings over railway lines has become a crucial concern. The project focuses on the installation of a pedestrian overpass that will enable safe and convenient passage for commuters over the railway tracks, reducing the risk of accidents and enhancing station connectivity. Scope of the project: the installation project involves the construction of a new pedestrian overpass spanning the railway tracks to link the two sides of the station. Pedestrian overpasses are vital structures in the railway environment, particularly for crowded stations like Sasaguri, where there is frequent movement of people between platforms. This overpass is designed to streamline passenger movement while significantly reducing the need for crossing railway tracks at ground level. Liebherr LTM 11200 NX. The crane of choice. A key feature of this project is the use of the Liebherr LTM 11200 NX, a state-of-the-art all-terrain crane with a lifting capacity of 1,200 tons. This crane is renowned for its high capacity and versatility, making it well-suited for handling large-scale infrastructure projects like the installation of bridge beams. The Liebherr LTM 11200 NX, with its impressive reach and precision, was an ideal choice for Sasaguri Station, where the beams needed to be carefully lifted and positioned above active railway tracks. Why the Liebherr LTM 11200 NX? This crane's ability to lift heavy loads with exceptional stability and precision was critical for this project. With its extensive telescopic boom and all-terrain capability, it provided both the range and flexibility required to maneuver in tight spaces. Considering the operational challenges, such as working in an area surrounded by railway tracks and overhead electrical lines, the use of a high-capacity all-terrain crane minimized risks and disruptions. The overpass installation involved planning and precise execution. Since the project required working above active railway lines, ensuring minimal disruption to the railway's schedule was paramount. Thus, the installation of beams and other components was scheduled during non-operational hours, typically late at night or during off-peak times when there were fewer trains passing through Sasaguri Station. During the installation process, the Liebherr LTM 11200 NX was deployed to lift and position the massive steel beams that form the core structure of the overpass. These beams had to be placed accurately to avoid conflicts with existing railway infrastructure. The crane's operator, supported by a team of engineers and safety personnel, lifted each beam and carefully aligned it into place, ensuring that it met the project's design specifications. One of the most crucial aspects of the project was maintaining safety standards. Working over active railway tracks demands strict adherence to safety protocols. The project team implemented a variety of safety measures, such as detailed planning of crane maneuvers, monitoring weather conditions, and coordinating closely with railway authorities to prevent operational disruptions. The use of the Liebherr LTM 11200 NX also contributed to the high safety standards. With its advanced features such as load moment indicators and computer-assisted controls, the crane minimized risks of overloading or operational errors. Additionally, the crane's robust design offered stability, even when lifting heavy beams at significant heights, reducing the possibility of accidents.